Good evening, Fang. Can you hear me okay? Can you hear me okay? Hi, Daniel. Can you hear me okay? Okay, I want to start desktop sharing. Can you see the desktop okay, Daniel? Very good. Welcome. So we have, I'm starting just a little bit earlier tonight, about a minute, but people will come in. Welcome, Daniel and Fang. I hope you had a great weekend. Before we begin, do you have any questions? Thank you, Daniel. I'm going to discuss Chapter 3. I've got a number of PowerPoints and slides and stuff, as well as the PowerPoint for Chapter 3 from the author. What's due at the end of this week is the homeworks 3 and 4 for Chapters 3 and 4. The CC Confer question. And I'll answer the CC Confer question this Thursday. Welcome, Karen. How was Test 1 for you guys? Good. Yeah, I always check the test questions to make sure that I've covered at least close to the concept. And I'll always tell you, you'll see it again, and I mean that you'll see it on the test. Test 2 is a little bit more challenging because it covers a lot more concepts, but by the time we get there to do this, you should be pretty knowledgeable about those ideas. From my perspective, I'm going to show you the results. I thought it was very well done. We received 23 A's. So what I did was I took the optional and added the regular score to get the 47. The maximum really is 45, so basically each of these people got 2 extra credit points, and these people got 1, etc. So there were 23 A's and 6 B's. That's almost 30. 30 is 75%. So 75% of the class got an A or a B. We had 3 C's. We had 5 D's. Excuse me, 1 D, 2 F's, and 5 didn't take the test. So there's really no makeup. I don't give makeups on these tests, but what I do give is I don't want anybody to fail the class. So I give on all of the tests, because sometimes, you know, the questions are pretty difficult to answer, or, you know, something happens. And I really believe that people should be able to get a C in the class. So what I offer is what I'm going to offer to you guys. Anybody who got less than a C. I don't offer this for C's and above. I only offer it to people that got less than a C. So to reach a C, subtract your points from 27. And on that number of questions, or do that number of questions from the end of chapters 1 and 2. None of what we did. The questions that I have, the homework questions, come right from the back of those chapters. So don't select those. But let's say you got 25 points, right? You would subtract 25 from 27, giving you 2, and you just have to answer 2 questions. So the way I want them is you write the question, so the complete question that you're answering, and the answer in an email to me. And on the subject, you need to tell me, make up for test 1, and ensure your name is the same that's in Canvas so I can give you credit. You have until the last day to turn in any work, so basically the end of the quarter, to turn this in to me. I will grade and add those earned points to the optional. For example, let's go down. I think somebody may have done some optional. No, the people that didn't do any of the optional. So, for instance, let's take this 14. Okay. Yeah, let's take the 14. Subtract 14 from 27 is 13. So they might do 7 from one chapter and 6 from another. And I would put in their optional here, I would put 13 points. So that would boost them to a C. So I do this for only the operating system class. I don't do that for any other class I teach. Is that clear how the way of getting to a C on any of this is going to be available to any of the 3 tests? Any questions on that? Hi, Jing Jing. Hi, Albert. Hi, Joan Yale and Karen. Thanks, Karen. Okay, well, if you missed my explanation, you can look at the review. But I thought it was a good showing. Now, let's look at the results by question, which I was kind of disappointed in one area. Overall, 80% is pretty good. On the true and false, you guys did really well. You got 77% correct, 94%, 100% on that question. Almost 90, 80. And then on the multiple choice, things seem to change. We only got 66%. You just had to find the 4 that were indicated on one of the slides I showed you. This was the, I think, most correct. 91% got this one. 77% got this one, for 2 types of handling interrupts. But this was the real bad one. 9% of you guys got this right. Only 3 people. This describes multi-programming. Without the whole concept of multi-programming, you wouldn't have program isolation. I could see where you might think that, but without program isolation, it's got to have multi-programming to have program isolation. So this is the environment that describes this and this, because without this doesn't make any sense. So anyway, what I'm thinking of doing for this, so the fact that this was such a bad question, was at the end of the quarter, what I'm going to do is I'm going to add 3 points to everybody's score. So this will be handled at that time. Whenever I have bad questions like this, that's what I'll end up doing. I can't throw it out because it's in the totals. There's really no way for me to throw it out. But what I can do is just add 3 points to everybody's score at the end of the quarter. That's easy to do. So that's my plan for this problem. All the rest seem to be pretty good. You guys picked it up pretty well. As you can see, 86% got full credit. These were the essay questions. 26 got full credit. 26 people, 74%. So 3/5 did really well. One of them I want to talk about. This one. On the essay, this was the most where I didn't give full credit. And the reason I didn't is because it came right out of the internet. And I said, don't take things out of the internet directly. Well, most of these came right out of the internet. I did give credit because it was correct, but verbiage, word for word, came right out of the internet. These 10 were the ones that looked on the session and took it from last Thursday's session during my review. And that's what I really was looking for. So these people got the full credit. I think most people did really well on this one. You see most people 30. So overall, I thought it was an excellent result. Any questions before I kind of move on off of the test one? Is that a no? You can't hear me, right? Okay, I'm just checking. You vote to move along. Okay. All right. Well, I want to make sure that people understand results. I'll go over the results of each of the tests. Okay, let's start chapter 3. This is kind of where it gets really fun, I think. The hardware is interesting, but how does the operating system, handle all this stuff? So we're going to start with processes. And remember, processes are equivalent to programs, which you're going to see. So we're going to cover the idea of process concept, process scheduling, operations on processes, inter-process communication, examples of inter-process communication, communication of client-server systems. We'll kind of talk around this one too. Okay, a lot of different definitions. A program in execution forms the basis for all computation. Okay, we need to describe the various features available, including scheduling, creation, termination, and communication. That's really the objectives of this chapter. So, what's a process? A process could be a batch system job. That could be a process. time-sharing system, user programs, or tasks could be processes. Textbook uses the term job and process almost interchangeably, so just be aware of that. Job really comes from the IBM world. Process is a program in execution. A process execution must progress in sequential fashion. And we'll talk more about that. Now, the three kinds of things that you find in a process would be the program counter and the registers that go with the CPU, the stack, and the data section. There's also, and I guess in the data section, he's including data and program. We'll talk more, or we'll see a better diagram of this. And here it is. This is a better diagram. This actually came from the Unix world, this diagram, where the text is the program code. All right? This is the program code. The data are all the definitions that the program code has defined. And then what happens is, as requests for either more memory or for operating system activity is pushed into, from the stack, pushed down, or it's on a heap moving up in memory. So this is kind of like a dynamic area of the system stack and the system heap. The data is typically the program's data area, and the text is the program's code area. Any questions of that? Okay, pretty easy. This is really the fun part. As a process executes, it changes state, because you have to know what's happening with the process. Is it a new process just being created? Is the process running on the CPU right now? Is the process waiting for some event to occur? Is the process ready to run if we had a CPU available for it to run? Is the process terminated? Here's a diagram of process states, and it's called the process state transition diagram. I have a one that you're going to see again, and you're going to have to know how to manipulate it on the test, and I'll show you that one next. But it's the same idea. You have new, goes through a ready, then goes to running, then gets interrupted, goes back to ready, or if it's running and requests service, it's now waiting for service. When the wait is over, it gets placed in the ready list to run again. If it's running and it's terminated, then it goes through an exit phase. And this is pretty basic. I'm going to show you a complete diagram in a minute, as soon as we get through some of the terms. Okay, the process control block, in terms of data structures, the operating system has many different data structures. The process controller, PCB, is one of those. And what's in it is the process state. Is it running? Is it waiting? What's the state of the process? The program counter is the next instruction to fetch, the CPU registers, the scheduling information for this process, any memory management information, basically pointers to the memory locations or the memory table, any accounting information or pointers to that data structure, and any I/O or device status that's pending is in this, and a lot of other stuff. You'll be seeing these again on the test, so you should know them. And here's an example. Process date, number, program, registers, memory, list of open files, etc. I want to stop a second. Any questions so far? Pretty straightforward, right? Okay. So, 16 general purpose registers. Your program counter is just one register or one special register, right? And then you've got this 16 or 32. I mean, it's pretty big. I'm going to talk more about where they're physically located. They may or may not be in this PCB. It depends on the operating system. Let me go back a diagram. A lot of times that is stored in the processes system stack area. The registers and stuff is stored there, not in the PCB, okay, in a lot of operating systems. But in this particular example, it's a simple operating system. They're going to stick the registers and stuff in the process control block. But it's big enough already to make it even bigger. It doesn't really make sense. Okay, the next thing is how the CPU switches from one process to another. We looked at it in Chapter 2, but we tried to show you how the interrupts allow you to get to the operating system. Well, once you're in there, what happens? What does the operating system do? And that's what we're saying is happening. Remember, we're only going to use a single CPU in our examples because it's really complex to use multiple CPUs. We will talk about multiprocessing, but in these examples, assume it's one processor because it's a lot easier to understand. And I'm going to show you in a better diagram than this. Okay, so you're going to have these scheduling queues. So you'll have your job queue, which is a set of all your processes. You'll have your ready queue, which is a set of all processing residing in memory, waiting, ready and waiting for the CPU. Then you might have device queues, which is a set of processes waiting for an I/O device so that it can do something, and processes migrate among the various queues. One could be running on the CPU and then go to the ready queue, then go back. We saw that in one of the process transition diagrams. Okay, example of a data structure. This is a queue, and you have a single link queue. You got a header, and then you have a single direction queue. So the head points to the first, and the tail points to the last, and then these point to each other. A lot of other systems use doubly linked so that you have a forward pointer and a backward pointer. Okay. In this example, it's only a forward link queue. Any questions on that? Has anybody taken a data structures class? That explains all of these different queues, stacks, and heaps, and all of different data structures, and how you manipulate them. It's a good class. It's not required for this because you can understand by just looking at this example how it might work. Okay, now, when we schedule the CPU, this might be a simple example. We have many processes that are ready to run, but we only have one CPU. So they stack up in here. We schedule one to run. It runs. And several things could happen. It could request service. Okay? Then it would go in and create an I/O queue, perform the I/O. When the I/O is done, it would go back to the ready queue. It could time out. This is a timeout event where it was running for a long time. The timer kicked off, the interrupt kicked off, and we put it as a time slice and directly goes back in the ready queue. Okay? Or we forked to create another process. So it's got to wait for that child to get created. And once the child's created, then we place the parent in the ready queue and the child in the ready queue. Or we wait for an interrupt of some event to occur, some kind of a time event that we had set. And that interrupt occurs, and we go back into the ready queue. So that's a simple way of showing the process state transition. Okay. There are three schedulers typically in most operating systems. The long-term scheduler or job scheduler, or from the mainframe, the terminology is master scheduler. So the master scheduler selects which processes should be brought into the ready queue to begin with. Okay, maybe the system is full and can't entertain another program. The user is clicking all over the place, you know, trying to run programs, and the master scheduler finally just says, nope, nope, I just don't have enough memory. A lot of times when you're in Windows and you double click on a program and you see the little hourglass going, that's the master scheduler determining whether it can run another program or not. Then there's the short-term scheduler or CPU scheduler, and we're going to know it as the dispatcher. This is the scheduler that determines which process gets the CPU next. Okay, very important. This dispatcher or short-term scheduler. And the third scheduler is medium-term scheduling, and it involves what's called swapping in and swapping out. The idea is this. The idea is the master scheduler says, hey, I could run this program, but I don't have enough memory. So I'm going to call the medium-term scheduler, or the swapper. That's another word for it. And the swapper will swap out an old process that's been waiting a long time for I/O or something. Swap that out of memory, and that'll give me enough memory to bring in a new program. And that's what this is about, is swapping out of main memory to bring in something else to execute. And of course, when it swaps it out on disk. Okay. Any questions? Okay, no questions. We're almost ready for an example. Yeah, this is a good place to stop. Now I want to show you the diagram that you're going to really need to understand. All of these are on this chapter as notes. Okay. This is the process state transition diagram. The circles are the states of the process. The green arrows are the transitions, and the red text are the schedulers. So I have the long-term scheduler. So it starts up here. The user wants to start a new program or task. So they're either on the command line or they're doing something, and it becomes new. And the scheduler determines, am I going to admit that into my system? In other words, do I have memory available for this guy to run? If I do, I will admit him and give him the resources that it needs in memory, because we don't know yet if it's going to need I/O or anything like that. So we give him the resources it needs. We put it in the ready state. Then the dispatcher, short-term scheduler, the dispatcher, out of the ready list queue, picks the next one to execute. And the dispatch changes the state. The dispatcher will change the state of that process to execute. And now it's running on the CPU, very happy. Okay. It may time out, meaning it's just maybe in a loop. Who knows what's going on? But the timer interrupt causes the operating system to decide that this guy is going out. So he time out, puts it back. Because if we gave it the CPU, it would continue to run. So it times out, goes into the ready list, and the dispatcher decides which one to run next. And it runs like that if it times out. Now what happens is it may not time out. It may request a record or open a file or whatever. Well, that's a service request. And we know we've seen those service requests. Those are on the Intel. They're at int21. So it would go to the operating system that handles a service request. I'm going to show you the other piece of this in a minute, but I wanted to show you first how the process transitions through these states. So it goes from executing to blocked or waiting. A lot of authors use waiting, and this author, I believe, used blocked, but this is either blocked or waiting, is this state. When the service is finished, it goes back into the ready queue because the service request is completed. So it goes back in the ready state. Now, if we need memory that's sitting there blocked, we need memory for some other process to admit, the intermediate term or swapper gets invoked, and it might pick that process that's blocked and suspend it. So now it's suspended block in this state. See, this line here represents whether the process is in memory or out on disk. That's what this line means right here. So it's sitting out on disk. Now, in a virtual system, I'm going to show you a different way, but let's assume this isn't a virtual storage system. We suspend that, and maybe that I/O completes. Well, it's not going to go here. It's going to go to suspended ready until the swapper decides that there's enough room in here to bring this guy back into memory and start him up again in the ready queue. Okay. It's also possible that if I have a process that is really low in priority, it's kind of a silly way to do it, but I have a low in priority, I might decide, and it's in the ready state, I might decide to suspend that, and that will release that memory, and then leave it out here for a while, and then when I have memory enough, I could resume that process, and it'll be back in the ready state. Okay? So I've gone through all of these states except this one. So I pick a process, the operating system dispatcher picks a process, go from ready to execute, and it's in the state executing. One of two things will happen to leave. One is a normal exit. In other words, the program does a return. When it does a return, it actually returns back to the dispatcher. Okay? And that's how it knows it's returning for that callback. And it could be that there's an error. Now, a different routine would handle an error in execution. It could be divide by 0. It could be a memory out of bounds reference for your program. It could be any number of errors. Well, if it is, then it's going to do an abnormal exit. And then it goes into what's called the terminated state. And then at that state, we release resources, etc. And that program's done. Is there any questions? Do you have any questions about this process state transition diagram? It's really critical that you understand it. Okay. Let's go back. Well, let's do, let me do another example. Yeah, this is a good example. Okay, I've got two programs. First, let's look at memory. All right? Let's examine memory. The way the hardware, now remember, the interrupts are really hardware. They're not software. They're hardware. So the interrupt vectors are specific memory locations in real memory, right here, in real memory. Usually they're at the high memory locations, or excuse me, low memory locations. That's usually where they're located. When the operating system gets loaded into memory, the very first one it boots up, it loads these handlers, like the timer handler, and the service request handler, and the I/O completion handler. It knows those addresses, and it places the addresses up here in the special memory area where the interrupt vectors can use. So all of the addresses that are, because remember, when the operating system gets rebooted, these addresses are going to change. So during boot time, when the operating system gets booted, the kernel knows where each of these are located because of these vector interrupts. Now the hardware uses these interrupts. Okay? So I'm going to take you through that in a second. So this is part of the operating system data structure right here, these handlers. And then I have the dispatcher is resident. There's a bunch of other routines that are resident in memory. They don't swap out or anything. Then you have your system data area, okay, for all your data structures. And then finally, when you start putting in user programs, they're in their own address space. And like program A has the code and the data, and it has a little area, the system save data area, that saves, it's where the operating system saves the state of that process whenever it's interrupted. So whenever a program is running along and gets interrupted by some interrupt of some kind, the operating system handler that handles that type of interrupt knows what program is running because it's in the execution queue, so it knows that program A is running, and it saves the state right here in that program's save area. Okay, program B, same thing. It has code and data and a system save data area for B. Okay, so let's see what happens. It says, who executes next? Program A started. Okay, we got a timer interrupt hit. So in other words, program A was running and it timed out. The timer is a hardware interrupt, and during the interrupt processing, it said, oh, I've got a timer interrupt, and vectors over here to the timer address of the timer handler. So it's going to save the current program counter. And that's what it does. It saves the current program counter in one of these registers, these vector registers, saves that guy, loads this address in the program counter. All of this is done in hardware, guys, no software. This is a hardware function. So it happens immediately. Flips the mode from user mode, because program A was running in user mode, and flips it to privileged mode. Okay? So now the timer handler is running. When it does what it needed to do, well, what's it going to do? Well, I've got to save the state. That's what these handlers do first. So let's think about that. In this area is the program counter that was saved. So it copies the address of that saved program counter down here for the program counter in the program A, because it found out program A was running on the CPU. Changes the state to ready, because it was a timeout interrupt. Changes the state of that process control block to ready, and then saves the registers. Okay, so it saves all the registers. Then it's going to call the dispatcher, calls the dispatcher, and the dispatcher chooses from the ready list. There's only A and B. Well, A just ran, so why don't we start up B? So program B is started. Okay, well, here's how it starts it. It restores the registers that are saved here. It loads the program counter for program B that was last used to fetch the next instruction. And when it loads that program counter, at the same time, it sets the mode to non-privileged mode, and now B is executing on the CPU. And what it wants is a service request. So it's going to be a soft interrupt because it's a program interrupt. Well, what happens? Well, once again, the interrupt scheme, the hardware, saves the PC, saves the program counter into a special register and loads the service request address for the service handler. Flips the mode from, once again, the hardware is doing this, the CPU is doing this, flips the mode from non-privileged to privileged mode, and now the service handler in the operating system is in there. First thing it's going to do is save the state of that running program, which happened to be B, because we know B was in state of program, in execution state. And then it saves the registers for, that's the state, the registers for that, before it plays with the registers. And then it needs to block that program. It needs to set up and start the I/O that it needs, because it wants a record or something. After it starts the I/O, it calls the dispatcher to decide what to run next. The dispatcher looks on the queue. There's only A in the ready state. B is in the block state. So program A runs and runs and runs. Let's assume that this I/O for B is completed. Well, that's an interrupt. That's an I/O completion interrupt to the CPU, which means we're going to do another of these swaps of hardware, of interrupts, where we save the current running program counter, we load the I/O completion address in here, and we flip the non-privileged to, non-privileged to privileged, and start executing code here. Okay? And what that code does is, oh, B was waiting, and the interrupt B means it's that I/O finished, I'll move it from the block or wait state back to the ready state, put it in the ready queue, and then signal the dispatcher or call the dispatcher to decide what to run next. And that's what happens here. Wow, is that a lot? Yes, the dispatcher chooses from the ready list what goes next. That is 100% correct. That is the role of the short-term scheduler. The dispatcher is the short-term scheduler, always decides from the ready list which process needs to execute next. If there are no processes, what do you think it does? When it executes, not where. When, Mega. It's always, it's not where. It's already in memory. Yeah, when. That's right. The dispatcher chooses when, or chooses which process in the ready state gets the CPU next. That's the role of the dispatcher. So you're right. If there's more than one program, then it's going to decide if A, B, C, or D should get the processor next. Now I have another example of this. In the notes, I wrote it up. So in the example, okay, let's not, this example is generic. This example is a generic example. Okay, there's a better example here. It's a little simpler. I've got the same notes, but I wanted to show the diagram with the notes with specific examples. So here's our notes. It's going to be tough to show both. I'm going to move this over a little bit. Now I'm not going to know if you're communicating with me, because that would be hard for me to see. So I'll ask to kind of hold your questions a little bit. Okay. So, same concept. Same concept. And this is called a context switch. When I move from one process executing to another process executing, the name of that is called a context switch. We're going to see that a lot in this chapter. So an example of a context switch from A to B. So the PCB, right, has information, A's PCB, has pointers to where the code's located, where the data, where the stack, and the program counter for A is located, and the current state is executing. B, in its process control block, has a pointer to the code, the data, the stack, and the program counters B, and it's in the ready state. Okay, the timer interrupt hits the CPU. The hardware switches the CPU to privileged mode. The hardware saves the current PC in a fixed location, up here somewhere, fixed location. Hardware loads the timer interrupt handler address, THA, I think I need to do the other example. I got the wrong one. Yeah, this is the one I wanted. I'm sorry. It's a little simpler. It's the same example. It's just specifying each of the steps. So the idea was this 3333 was program A's current address, and this 2220 was the timer handler address that was in fixed location. So what really is happening when a timer interrupt occurs, remember we're in non-privileged mode running program A, so it's at this location in memory. The hardware stores the current program counter in the saved program counter area. It loads this address, the timer handler, into the program counter, flips the mode to privileged, and starts executing. Okay? So the timer handler hits the CPU. Hardware switches the CPU to privileged mode. Hardware saves the current PC in a fixed location. Hardware loads the timer interrupt handler address, the 2222, and starts the CPU on a fetch. Now it's running the handler in the kernel area, and it is running it starting at this address, that handler, checks the execution list, finds A is executing, looks up PCB A. Now it knows where to save the stack. It's down here in this process stack. Saves the saved program counter, this guy up here, saves it in the system stack, and then saves the registers. Changes the state of A from execute to ready, adjusts the queues, and then passes control to the dispatcher. Now the dispatcher chooses the next process to execute from the ready queue, and it chooses B. There's only two in this example. And places it in the execute state, so it changes B state to execute in the process control block. Remember, the process control blocks are up here in memory, right here. I don't show them in this example, but the process control blocks are up here. These are the program areas. So we have, in the process control block, we have pointers to all of this stuff that's part of that process. Places in state, loads the register. So here's my saved register. So it restores the registers first, and then it finally loads this address, 5050, into the program counter, and flips to non-privileged mode, and bam, it's executing program A now. Okay, I'm going to move this so I can see any questions. Any questions on this example? Okay. Let's take a look at the data structure. So a simple data structure would be, I have a specific location where the operating system tables start. So that data structure, my guess, would be somewhere right in the known area of memory for the resident memory for the operating system. That pointer would be somewhere in there, because you'd have to know where that data structure starts. Okay, so I have a system pointer, basically. And that system pointer points to everything in my data structure that I'm going to keep track of. The process control blocks, once again, the process control blocks. Let's go back and look at those. That's the I/O device blocks. Did I miss it? Oh, I guess I don't have a structure there. Yeah, it could be very similar. I would have a process control block pointer, just like I have this. Here they are, process control blocks. They point here. But that's the data structure I'm trying to describe here. You have that pointer, you have your device control block pointer, you have your operating system cues, like ready, block, all of those states, those would be cues. The fixed address locations, you need to know where they are, and the vector interrupt that forces the CPU to save the current program counter in this temporary area and then loads the address of the interrupt handler. And I would have different addresses for each of my different handlers. And of course I have my 3 schedulers. Okay. I want to stop a second. Anybody confused? By order, you mean the order of things, the way things happen here? This order of events? Or the, yes, okay. Yeah, that's going to take some time to look at and analyze. And you do have the you do have the same text here. See, I put the same text here so that you could follow that example. When you take a look at this diagram. We'll go over it again because it's a key concept. How do processes switch from one program to another? That's called a context switch. I'm switching the context of what is executing. And all the little detail that goes along with it. Okay. Normally, when you design your operating system, your user processes are in virtual memory, and some of your operating system procedures are in virtual memory, but all of the key operating system tables and routines typically are resident memory. They're not virtual storage, and there's a reason for that. And I'll illustrate that when we talk about virtual storage concepts. But it's just much faster if it's in real memory, not virtual memory. So when we do talk about memory management in Chapter 8 and 9, I'll tell you the difference. I'll try to describe the difference between real memory and virtual memory. Yeah, it's a big concept. But normally, user programs are in virtual memory. I don't know any that are in real memory. Unless your compiler, you might be able to do it. You might be able to write a program that will be loaded into real memory. That might be possible. It depends on the compiler and whether your operating system supports that. Okay, that's that. So let's go back to the slide presentation, because there's more to talk about. Okay, here's the book's definition of a context switch. When the CPU switches to another process, the system must save the state of the old process, that's what we were talking about, and load the save state for the new process via a context switch. Context of a process is represented in the process control block. Context switch time is overhead. The system does no useful work while switching. So what it's saying is, when an interrupt occurs, and I'm going to switch from A to B, everything you see here is no work done on user programs. All of this is operating system. All of this is operating system. And finally, we start up user program. So real work is being done here. All of this is called a context switch, and it is overhead. And you've got to take it into account, and it's got to be very well designed, which we're going to talk about over time, because it's a fascinating topic. How do you make the most of this overhead? Okay, so process creation. That's, you can create children processes, which in turn create other processes, forming a tree of processes. Generally, a process identifier and managed via a process ID, and you've seen that. I've shown you that. All processes, I'm going to show you all the processes that are running right now in my system. I've got 123 programs running. You can see them here. And they all have an ID. And ID 0 is a special process. It's called the idle process. And if I do it by CPU, see, the idle process gets a large percent of the CPU. And that's what I was trying to say or ask a while back, is if you don't have anything in the ready state to run, what would you run? What would you execute? And one tact is run an idle process until some interrupt occurs of some kind, in order for you to, do a context switch. Okay. Resource sharing. Parent and child share all resources. Oh, this is a question of design. How would you design sharing resources? Does the parent and child share all resources? Do the children share subset of parents' resources? Or parent and child share no resources? How would you implement something like that? Or would you? Or why would you? So a lot of the stuff that we're going to see will be design choices. Execution. Does the parent and child execute concurrently? Does the parent wait until the children terminate? All of these could be features of your process. So you might say, well, I'm going to allow both of those. In other words, when a child is created, I will tell it through the API that you can run it concurrently with the parent. Or I'm going to tell it through the API that the child has to terminate before the parent can run. So you could include both of those. Okay, same thing here. You could make it so that all three of those things are possible. They're using an API, but imagine the effect of the operating system and how do people utilize those features. You know, programmers. How do programmers utilize those features? The more complex you make it, the more difficult it is for programmers to manage. Same thing with the address space. Does the child get a duplicate of the parent, or does the child have the program loaded into where the parent is? This is just an example of a system call to create. It's called a fork in Unix. In Windows, it's create new process or some kind of API call like that. Okay, and there's just a diagram of it. You know, this is not that exciting, so I'm going to keep going. I do want to mention this. If you has anybody here not seen C code? And this is new to you. Anybody here? No? Wow. Good. I'll just point it out to some people that may not know. I don't ask you to code C code unless you're going to do the special project. Okay, if you're going to do the special extra credit project, then you're going to program in some language, and I don't really care which language. But we are going to see some samples of code, and it'll look something like this. So I'm just going to point out the concept. You have the main program, and you have braces. So this is the end of the brace. This is the beginning of the brace. This is an entry of a variable. Looks like PID, PID1, PID. It's a variable that points to this data structure. It's PID data structure. And then it links one to it. Okay, if in parentheses, and then the beginning of the code is the brace, and the end of the code is another brace, and it looks like it's right here. So usually they line up. So if this is true, it does this stuff. Else, if this is true, it does this stuff. Else, it does this stuff. And that's about what you would run into in our book. Our book might use these examples. And I think I went over some of the key points about this language. Okay, I'm going to skip over Solaris. Now, when you terminate a process, you're basically issuing an exit or some abnormal termination. And the issue really becomes here if you have a parent and children both executing, and how do you handle the death, if you will, of a parent or a child? How do you handle that in your operating system? Okay. Some operating systems do not allow children to continue if its parent terminates. So what happens if the parent terminates? It goes and terminates all the children. Some operating systems use that concept. Some operating systems allow children to execute and continue executing without the parent. So you got to determine if you're going to do that or not. So it's another design question. It's more complex. Okay, now we're moving into a different area. We're kind of moving away from this concept of processes and their transition to how a process would communicate with each other. So they could be independent or they could be cooperative. Excuse me. A cooperating process can affect or be affected by other processes, including shared data. When we talk in memory, we'll talk a little more about sharing memory. But these might be reasons for cooperating processes. You have information sharing. You have computation speed up, because you could have two processes executing computing something. Maybe more modularity, better design. It's a complex, and so you divide it into, this guy's going to do this guy's going to do that kind of thing. And finally, it's convenient if you're going to share data. Cooperating processes need some sort of inter-process communication, IPC. And the two methods of IPC are either shared memory or message passing. I remember very clearly the Sun environment when I was managing the Sun boxes. They used in Informix database was what we used on the Sun box. And Informix used shared memory. So when we installed Informix on our box, we had to allocate a special shared memory location through the operating system. And that's how the different pieces of Informix communicated with each other. The other method is message passing, and quite a few operating systems use this. So here's the two models. And you need to know this model so you could explain it, or this model. So if I'm going to pass a message, I would write a message, and then this process A would read the message. So it looks like process A is writing the message, process B is reading the message. So one of them in this message, and think about the email. Email is a good example of this. Where you email somebody, right, and then you have to kind of wait for them to pick it up, right, and pick it up. That's really this model of messaging. So if this guy is waiting for a message, it's going to have to wait in the wait state for the message to pop in. That's how this would communicate. Shared memory concept is process A and process B are sharing this block of memory, and they're communicating through that block. It's faster, it's synchronized, except, you have the same kind of issue, is this the current information for B? So A writes that E has to know that that's been written so it can pick it up. So there may be some lag time here, and there may be lag time here. Same concept. Is that clear? I was kind of muddled in that. Okay, thanks. Yeah, I just want to make sure it's clear. So let's look at cooperating processes. Independent processes cannot affect or be affected by the execution of another process. Cooperating processes can be affected. So there's times when you have to sync up the two processes. Oh, I love this problem. What he's telling you now is how cooperating processes can produce information that's consumed by a consumer process. So you have this concept of producer and consumer. And there are two mechanisms. One mechanism is called unbounded buffer, meaning there's no limit on the size of the buffer. Bounded buffer assumes there's a fixed size. And the example preceding us, this typically is a fixed size buffer that you're using. This might or might not be. Hard to say. Okay, now using the shared buffer, right? We can show how we use a bounded buffer of size 10. We're going to come back to this producer-consumer problem in Chapter 6. So I'm not going to spend a lot of time on it with you, but I just want you to understand the idea. I don't know if there's a good diagram. Let's see, there might be a diagram. I like diagrams rather than the code. No, I don't see one. Let's go back here. See if I have. Yeah, I do. I thought I did. A spooler on your operating system. The spoolers typically are for print spoolers. But the concept of a spooler is you're buffering different speed devices. That's really what a spooler is doing. It's buffering different speed devices. For example, if we go way back to card readers, you guys probably never seen a card reader, but I remember card readers where you put the cards in the card reader and then flip through them, and as it's flipping through them, it's writing disk data of the same card. So it's taking that slow read a card, read a card, read a card, and going into really fast memory. Another example is printers. Printers print really slow compared to memory. So you have a spooler called a print spooler, and it has the concept of producer-consumer. So, for example, if your printer has a buffer of 100, your producer code would send this data to the buffer and stop when it reached the point of which it needs to have the consumer take it off. So there are flags with this. Okay, so it'll fill the buffer until it needs to stop because the consumer hasn't taken off the 300 or the 400 yet. Okay, so it filled 5 and 6. What you don't see is the previous, I guess. I didn't show the previous. Because the consumer is the printer and it's running slow. So it looks like I filled 1, 2, 3, 4, and the consumer took off 1, 2, 3, but hasn't taken off 4. So I would fill 7,000 here and 8,000 here once they've been taken off, and then I would wait. If he hasn't taken off 5,000, I would wait as the producer until the consumer took the 5,000. Multi-threaded program. Your spooler could be multi-threaded, yes, sure. That both these threads are executing on a singular buffer. That's the concept. But like I said, we're going to see it clearer in chapter 6 or 7. It's one of those chapters. But I want you to understand it. So let me go down here to make it easier. Let's do it this way. Let's see. So I might produce 9 items. Let's say my buffer is 10. That's an example. Okay, the producer produced 10 items. The consumer is running much slower, so it did item 1, item 2, item 3, and I come back to the producer, and I know that it pulled off this, so I'm going to make that 11, 12, and this would be 13, and I have to wait until the consumer picks up 4 before I write that. So the consumer is going to pick up 4, 5, remember it's running much slower, 6, 7, 8, and maybe it times out. Okay? So now I can write 14, my producer, 15, 16, 17, 18, but I can't, 18. I can't write 9 because the consumer hasn't taken it off. Do you see how this works now? Good. What this is that even though it may be the same program, it is maybe different threads, or it could be 2 different programs. You cannot predict the speed of these. That's the key concept. I'm going to come back to that when we talk in chapter 4. It is a real fun topic. Okay. So if we take the other approach, message passing, right, you're going to have a send message and then a receive. So you could have a P and Q wish to communicate, so those are two processes. They need to establish a communication link and exchange messages. So you can do the communication link physical, shared memory, hardware bus, or logical, using properties in the operating system. Okay, what you have to do, see, these are implementation questions. Yes, Dale, it is exactly a circular FIFO buffer. Yes. How are the links established? I mean, you got to determine that. Can a link be associated with more than two processes? Can you allow 3, 4, 5? Every time you increase the capability, you increase the complexity. Keep that in mind. How many links can there be between every pair of communicating processes? So you could have A and B talking to on 2 links. How big is the link? How much can you store to communicate? Is the size of the message that the link can accommodate fixed or variable? Is the link unidirectional or bidirectional? All of these are implementation questions that the implementer has to decide on when they design their operating system. Okay, if I'm going to choose direct communication, I would have these properties of a communication link. First, they're established automatically. A link is associated with exactly 1 pair of communicating processes. So a link is equivalent to 1. So I'm defining what I mean by this. Between each pair, there exists exactly 1 link. So I can't, between 2 processes, I can't have more than 1 link. And the link may be unidirectional, but usually bidirectional. So I'm going to allow bidirectional links. So I could send, P could send a message, Q could receive a message, Q could send a message, and P could receive the message. That's bidirectional. Any questions so far on direct communication? Thank you. Okay, so indirect is you've got an intermediary. You've got some kind of a mailbox or a port is a good mechanism. And each mailbox has a unique ID or a unique port number. Processes can communicate only if they share a mailbox. Same rules apply. However, a link can be associated with many processes. That's because you're using a unique ID or a port. So in this concept, I have to be able to create a new mailbox. I need to send and receive messages through that, and I need to destroy the mailbox. So I might have these primitives that I have in my operating system, and then I would give the programmers APIs to execute this stuff. Okay. Sharing a mailbox. Okay, P1, P2, P3 share mailbox A. P1 sends, P2 and P3 receives. Oh, say P1 sends, P2 and P3 receive. Who gets the message? You see the complexity here? unless I specifically specify P2 or P3, how would you allow them to receive the message? Okay, one solution, allow a link to be associated with at most 2 processes. Allow only one process at a time to execute a receive operation. Allow a system to select arbitrarily the receiver. So the system would pick P2 or P3 to receive it. And the sender is notified who the receiver was. So in this case, if P2, we picked P2, we would return a message to P1 saying P2 was received the message. You see the complexity of this. I'm talking about it at a high level, but to implement this takes quite a bit of thinking. Okay, we're going to talk about asynchronous and synchronous. If you think about these concepts, when it's synchronized, blocking is considered synchronous. So let's see what that really means. A blocking send has the sender blocked until the message is received. That makes it synchronized. So basically what happens is if process A wants to send a message to process B, and we're using this blocking, what's going to happen is it'll issue the send message and we'll put the process in a block state, waiting for the other process to receive it. Same thing is true here, is if I'm receiving a message and I haven't received it, we put the process in a block state until the message is available to be received. So that's what blocking is about. We put it in a wait state. Okay, now we're not going to block the processes. Okay, so it's no longer going to be synchronized. It's going to be asynchronous. Okay, so what we happen here is we send a message to A sends a message to B, and we continue running. And then we request a message to be received, right? And we keep running. We either get a valid message or we don't get anything, but we keep running. This asynchronous mechanism is a lot tougher to implement. Because how are you going to get them back together? Because the whole concept of communication is one sends, one receives, right? That's the whole concept between message passing. But this one is a tough one to implement. We talked about buffering before. One, bounded capacity, so there's basically a finite length of messages allowed. This may or may not be true. The sender must wait if the link is full. That may or may not be true. I suspect it's easier to implement that once the message is filled, it sends the link. The unbounded capacity is an infinite length, and the sender never waits. Tough to manage unbounded capacity, because I guess when you're dealing with memory, that's how you're going to pass this around. You have to worry about running out of memory in an unbounded capacity. Okay, here's some examples. POSIX, operating system, concepts. Use this. I'm not going to get into this because I don't have anything of this detail on a test. What I want you to understand is the concept of inter-process control. What communication? Inter-process communication. And I'm really interested in that you understand the shared memory or messaging. I'm not going to ask, code up something. Mock was a training operating system that was built a number of years ago. I don't know if it's still around or not. Okay, so local procedure call is one way to pass messages in Windows. I'm not going to spend a lot of time on this one with you guys. The reason is, in your projects, which I'm going to discuss after test 2, in your team project, I have 2 projects. One is a coding project that's extra credit, and a team project that's not extra credits required. But on the team project, you're going to tell me things like, if you pick Windows, this kind of thing. How does IPC work in Windows? So I'm not going to go at any depth in this with you guys, because I would expect that you're going to do that. But let's at least go through what we're talking about. Okay, so I have a client server, or basically I have some program and another program. Let's think of it that way. And I have connection ports. So I'm going to create a socket, basically, with that port. So that socket can communicate with the client and the server. And we use ports and sockets all the time to communicate. Do you guys know what, well, let's go to the next slide. It might help. So we'll talk about sockets a little bit, remote procedure calls, and remote method invocation. Take a look at those. It's defined at an endpoint for communication, and it's basically an IP address and a port. So I have an IP address, a colon, and a port number. So it refers to 1625 on this host. And communication consists between a pair of sockets. And do I have? I was going to illustrate this with you. Let me start. Something. I want to start a MySQL. I'm going to start MySQL, which is a database engine that communicates with the client through a port. I'm going to show you that. I have programming tools. These are all my programming tools. WAMP is a Windows process. Did I just lose you guys? Yeah, I thought so. Yeah, that happens when it tries to go outside. Let me reconnect you. Okay, do you see it again? Okay. Yeah, I should have remembered that. Whenever it does a monitor change of depth, change of depth from one mode to another, we get that. Anyway, I did start it, and it's right here. And I'm going to go to MySQL ini file and open up the ini file. And you see the port it's using is 3306. And that's the port that the server is using to communicate to the client. So this daemon or program is communicating through that port. And it opened this socket, which is a file. And when the client requests service, it goes to that port, and then the port returns the database results through that socket. That's how it communicates. Has anybody else done any database stuff? Good. Have you used MySQL? Excellent. The other thing, since we're here, I wanted to show you is I want to go to the C drive, Windows folder, System 32. System 32. Drivers. And you can do that on your Windows machine. etc. And there's where your ports are identified, and it's under services. So I'm going to send this to Notepad. And you can see the different port numbers. They're pre-assigned. And if we look, you don't see 3306 because it's a dynamic port that got created when it loaded the program. So these are ports that are pre-identified. So if somebody's using these ports, you can remove them for more security. But normally these ports are monitored by your internet protection, your firewall. The firewall looks at those external ports to make sure that things don't get out of hand. And port 80, as you might or might not know, port 80 is your HTTP port that talks to the web browser. Okay. Just that's like an aside. It's always good to show examples. Okay, let's see what else we got. And there's an example of a socket communication. And they're showing the web server. Okay, another mechanism is remote procedure calls. You know, I don't use these very often, but you have to, if you're going to use remote procedure calls, you have to pass parameters. And the whole idea of marshalling parameters is quite a design issue. And here's an example of an execution of an RPC And the final one we're going to look at is the Java stuff. You've got your program, and then you've got your Java machine to talk to. Another mechanism. It's pretty cool. And I think, oh, that's right, it did talk about marshalling parameters. This isn't going to be on the test. I'm not going to do marshalling parameters. Just a little more complex than what we really need to worry about. Okay, that's the end of Chapter 3. So let's look at the key concepts of Chapter 3 and review that. We have about 15 minutes. First one is this. The operating system has to maintain what state the process is currently in. It starts at new, and the master scheduler determines if it can enter and really start running. So, be ready to run, I should say. So if it has all the resources it needs, meaning memory, then a process is changed to ready and placed in the queue. The dispatcher is working like the devil to decide which process out of the ready queue gets executing next. Okay, that switching from one process to another on the CPU is called context switch. The dispatcher is the short-term scheduler that decides which process gets the CPU next. Okay. During the time it decides, and we're going to talk about the algorithms in Chapter 4 and 5, I think. I think 4 is about threads. 5 must be the algorithms that the dispatcher would use to determine which one to run next. Okay, and those are always fun. So it goes through those steps. Well, what step does it go through? What steps does it go through? Dispatcher chooses the next process to execute from the ready list. It removes that process from the ready and places it in the execute list. So it changes the in the process control block for that process it chose, it changed the state to execute. It looks up the system area, the system stack from that program, looks up where the registers are, stores loads the registers in the CPU, sets the timer mechanism, the quantum, for that, whatever the quantum time is that allowed that guy to run for a period of time, it's going to set the timer to that amount. It loads the saved program counter from the B's system stack area into the CPU, and it switches from privileged to non-privileged mode, and now that other process is executing on the CPU. Is this clearer now than before? Is it getting clearer? The steps taken? Thank you. And I illustrated that process here. So go one more time. Program A is running. The address it was at, the last instruction or the next instruction to fetch is 3333, and the interrupt hit. It was running in non-privileged mode. The timer interrupt hit. So the hardware does the switch, saves the 3333 in a special place in memory, and it loads the timer handler address into the program counter, flips it to privileged mode, and then executes. Now it's executing in the handler in privilege mode in the kernel, and the kernel's going to save this state of the program counter, saves that down here in the program that was running, the system stack area, saves that program counter down here, and then saves the registers, because you don't want to do anything to the registers, so you save the registers. Now you handle that particular interrupt. Okay? So basically save the state of the program that was running, and all of that is overhead. Everything we just did was overhead. Context switch is overhead. I hope I showed all of the different diagrams. Yeah, I showed that one. I showed that one. And I showed that one. I know we went through this one as well. They were all pretty much the same example, just looking at it a little differently. Okay, are there any questions? Okay, what I'm going to say is, for the test, you really need to understand how this works. Okay? You need to understand the idea of a context switch. You need to understand the state, process state transition diagram, what's in a process control block, what are the items in the process control block. And I think that's it for chapter 3. Oh, there's a graph, 331. Golly, I apologize. I converted this from Catalyst, and it was supposed to convert correctly. I went through it, but I missed that. So let me check that real quick with you. While you're still here with me. Yeah, once again, I thought you guys did really well. I mean, 75% of the class got an A or B. Over 50% got A's. That's really good. Just be aware that the tests get a little tougher, you know, because the material is a little more complex. But then again, we're not going to spend a lot of time anymore on hardware other than what I just talked about, the interrupt stuff. Homework chapter 3, right, you said? There are some conflicting information in the slides regarding one of the questions. Well, you have to tell me which question, so I know. Yeah, you certainly need to to have that figure, 331. I'll look it up and put it in, okay? Or I'll change the question, one of the two. If you've already answered it, that's fine. Yeah, that's fine. But I'm not sure I'm following, Miguel. I'm not sure I'm following your question. Which question? Oh, from the test. From the test. Okay. Yeah, if you could find that, and I guess, was it chapter 1 or 2? Oh, you're still looking. You don't know. Sure. And we can discuss it next time too, you know. You don't have to worry about it tonight. Were you here during the whole discussion of the test when I reviewed it? Oh, I see. Yeah. Okay, yeah, if you could point that out, I could fix that for the next time I use those slides. You bet. Anything else? That's very helpful, you guys. When you find little errors like this, it might happen. Yeah, please do. Yeah, an email would be great. I'm just looking at the questions for this particular chapter, and yeah, I'm going to have to find that figure and put it in here. Or I'll change the question, one of the two. But this is good. This is a thoughtful one. No matter what you answer, I think, you know, as long as you think about it, and I've told you this before, that you could go on any of these solutions. You could, if the book says, well, why would you go that way? Either answers I'm going to look at, and if it makes sense, it's going to be correct. Because the whole idea, as you'll start to see, is there's all kinds of choices that you can make in your design that cause certain things to happen. And there's no right or wrong. All right, guys, I think we'll call it for this evening. Thank you for participating, and I look forward to talking about Chapter 4 with you on Thursday. No, you can always save, right? You can always start and save. You don't have to submit it. You could save your answer. The way it works is if you answer something, it saves it until you submit. So, yeah, go ahead and answer the ones that you can answer and skip number 3 until I fix it. Sure. Yeah, because I'm not going to change the others. The others look good. I spent tonight talking about this. What you want to do is you want to look up the system or read about it in the book, because the book has this. I don't cover this. This is an old operating system. I don't cover it now. But it's a good thing to look up. All right, guys. Thank you. I'm going to turn off desktop sharing and the recording. Good night, all.